Okay, here, question 2.3, we want to calculate the energy of the signal. And to calculate the energy of a signal, like signal xt, we use this formula. All right. So first of all, we need to define xt, to describe xt. Well, based on this diagram, we can say xt from the time 0 to 2, the value of the xt is 1. So xt is 1 if time is between 0 and 2. And then from 2 to 3, xt, the value of the xt signal is -1. So it is -1 for t between between 2 and 3. And from the time after 3, it is 0, so for t larger than 3, or for t smaller than 0, again the value of the signal is 0. So we have these 4 regions, and we now know the value of the signal at this time intervals. Okay, so I can then write the formula for energy of the signal xt like sum of, instead of I take integral from -infinity to infinity, I can take integral over these 4 regions. Okay, so instead of saying -infinity to infinity, I can say integration of the signal from -infinity to 0 of xt, absolute of xt squared dt, plus from 0 to 2 and then from 2 to 3 and then integration from 3 to infinity. All right. So here, instead of xt, I can put its value, and its value in this interval is 0. Okay, so we would have absolute of 0 squared, which is 0. And for the one here, in the time interval from 0 to 2, the value of the signal is 1. Okay, so instead of absolute of xt squared, we would have absolute of 1 squared, which is 1. And for this one here, we have absolute of -1 squared. And for this one here, we have absolute of 0 squared. Okay, so I can replace this. I can say e of xt equals integration from -infinity to 0. Well, I can't write it here. From -infinity to 0 of 0 dt plus integration from 0 to 2 of dt plus integration from 2 to 3 of dt plus integration of 3 to infinity of 0 dt. Okay, and well, obviously these two, the integration is 0 here and the integration here is 0, so we just have these two integrals. The first one, the integration of dt, is t from 0 to 2 plus, again here, the integration of dt is t, but the interval is 2 to 3, so we have This equals, I replace the value of t minus 2 minus 0 plus 3 minus 2, and this equals 3. So we can say the energy of this signal is, the signal represented here is 3. Okay, part B. I can do the same here. So we have 4 intervals actually. So I can say xt equals 0 if t is smaller than 0. The value of the signal is minus 1 if t is between 0 and 2. The value of the signal is 1 if t is between 2 and 3. And the value of the signal is 0 if t is larger than 3. Okay? So if you check, this is actually inverted version of the previous signal. Okay? I want to see if the energy of the inverted version of the previous signal is the same as the energy of the original signal or not. So let me again calculate that. So we know the energy of the signal equals integration of over these 4 intervals. That's from minus infinity to 0 of xt squared dt plus integration from 0 to 2 xt squared dt, integration from 2 to 3 plus integration from 3 to infinity of dt. Okay, so now I replace the value of the signal in these intervals. So we can say the energy of the signal at these intervals is alright. For the first interval, we know the value of the signal at this interval is 0. The value of the signal at this interval is minus 1. The value of the signal at this interval is 1. And here the signal is 0. Input signal is 0. So here we have integration of minus infinity to 0 of 0 squared dt plus integration from 0 to 2 of minus 1, absolute of minus 1 squared dt, and so on. Right, so if I replace if I calculate these integrals in these 4 intervals, well, first of all, we know that this is 0. We know also that this one is 0. So what we have at the end is the energy of xt equals integral of, well, the value of this one is then plus 1, and the value of this one also is plus 1. So we have integration of 1 times dt. Then I don't need to write that the 1 here. So it is from 0 to 2 dt plus integration of 2 to 3 dt. Well, we know the integration of dt is t. So we should calculate that in this interval from 0 to 2. And for the second one, the interval is 2 to 3, which is 2 plus 1, which is 3. So you see that the energy of the inverted signal and the original signal are all the same. So inversion doesn't change the energy of the signal. This one is time shifted of the original signal that we saw in part A. And we want to see if time shifting would change the energy of the signal or not. Again, we have 4 intervals from, I would say, the value of the signal t before 3 is 0. For the interval between 3 to 5, the value of the signal is 1. Interval between 5 to 6, the value of the signal is -1. And for time interval after 6, the value of the signal is 0. Alright, now I can write the energy of the signal as the sum of integration over these 4 intervals. Okay, so I can say energy of the signal is integration of the signal, integral of the signal from -infinity to 3. So this time then I think we know how to actually go step by step, so I skip the second step and directly write the value of the signal here. The value of the signal in this interval is 0, so we have 0, absolute 0 squared dt plus the integration in interval 3 to 5 of 1 squared dt plus integration from 5 to 6 of absolute of -1 squared dt plus integration from 6 to infinity of absolute of 0 squared dt. Okay, well, we obviously know that the value of this part is 0 because integration over 0 is 0, and the same for here. The value of the signal here we know is 1, and the value of the signal here is also 1. So I can, if I replace that, then I can write the energy of the signal equal to 0 plus, okay, we have integration of dt over this interval, which is t from 3 to 5, plus integration again, integral of dt is t, but interval is 5 to 6, so it is t from 5 to 6 plus 0, and this equals 5 minus 3 plus 6 minus 5, which is 3. So you see that the energy of the signal in this time shifted version of the signal actually is equal to the energy of the original signal. So time shifting doesn't change the energy of the signal. And the last part here, we have a amplitude scaled version of the original signal. Yeah, if you look at the original signal in part A, let's get back here. You see here the amplitude of the signal is from -1 to 1, okay? But in part D we have a amplitude scaled up version of the original signal, and the amplitude of the signal is from -2 to 2, and we want to see if amplitude scaling will impact the energy of the signal or not. So we saw that the inverting or time shifting doesn't change the energy of the signal, but let's check for amplitude scaling this time. Okay. Well, I can write signal xt in 4 different intervals. Well, if t is below 0, the value of the signal is 0. If the interval is between 0 and 2, the value of the signal is 2. If t is larger than 2 but smaller than 3, the value of the signal is -2. And if t is larger than 3, then again the value of the signal is 0. Okay, so the energy of the signal equals integration over the value of the signal in these 4 intervals. So it is integration from -infinity to 0 of, well, what is the value of the signal in this interval? The value of the signal is 0. So we have absolute of 0 squared dt plus the next interval is from 0 to 2. Okay, and the value of the signal in this interval is 2. So we have absolute of 2 squared dt plus the next interval is from 2 to 3, and the value of the signal is -2. So we have absolute of -2x squared dt, and the last interval is from 3 to infinity, and the value of the signal is 0. So we have this. Okay, and obviously the value of the signal here is 0, and the same here, the value of the signal is 0. Here we have 4 and the same 4 here, so I can write the integration, or I can write E of energy of xt in this way: 0 plus integration of 4 dt from 0 to 2 plus integration of 4 dt from 2 to 3 plus 0. Okay, so if I calculate the integration, it would have 0 plus 4t, because an integration of, well, I can write this like 4, I can take out 4 and write it like this: 4 times integral of 0 to 2 of dt. Okay, and we know the integral of dt is t, so we have 4t from 0 to 2. So plus 4t from 0 to 2 plus, again, we have another 4t, this time from 2 to 3 plus 0. If I calculate this, then you would have 8 minus 0 plus 12 minus 8, that equals 12. So you see that we doubled the amplitude of the signal. We doubled the amplitude of the signal here compared to the original signal, and its energy is quadrupled. Okay, so we can conclude this: if you increase the energy of the signal, if you double the energy of, if you double the amplitude of the signal, its energy will be quadrupled. Okay, so that's the end of this question. And we generally can say that if you multiply the amplitude of the signal by a, then, so let's see amplitude energy. Okay, if let's say we multiply the amplitude of the signal by a, then the energy will be multiplied by a squared. Okay, so we can conclude this.